Let's do a little homework help for chapter 6.1 part 1. There might be a problem like this there. A big thing in u substitution is what do I make my u? And sometimes it's hard to see kind of what the inside thing is. So rewriting it can help sometimes. So if I write this as exp root x, that's another way of writing the numerator. And then instead of dividing by root x, what if I do times 1 over root x dx? Does that kind of offer a suggestion for what's the inside thing and what's the outside thing? If you had a problem like the integral of something over root x to the 9 plus 5 dx, you could rewrite that as whatever that thing is, whatever that numerator is, times x to the 9 plus 5 to the negative 1/2 dx. Does that kind of give an idea of what the inside thing might be? Another idea you can try is anything that's fairly simple to take the derivative of might be useful as a u value, because you know you're going to have to take the derivative of u to get du, right? So if you see anything that's simple to take the derivative of in the problem, like u equals log x, u equals sine x, those can be helpful things to try for u. Let's take a quick look at something like integral of e to the x over 1 plus e to the x. What's my inside function here? Well, one guess might be that anytime we do e to the stuff, then that stuff is the inside function, right? So we might say try u equals x, because x is inside the exponentiation. But then you'd say du equals derivative of x times dx, which is just 1 times dx. And at that point, you're just changing letters. It's like doing a search and replace in a word processing document. It doesn't actually change the math problem. So this is not helpful in u substitution. It's just changing the name of the variable, which doesn't make it any easier to integrate. Now, I'm not saying it's never helpful. It turns out in Calc 2, when you're doing integration by parts, using u equals x can be quite helpful. So let's write that down. So it's not a general principle that it's never helpful to say u equals x, but we're using u in a different way when we do that in Calc 2. So what else can we do here? Could we say anytime you see a denominator, you could think of that as an inside function? And maybe that's more obvious if you do like let's do 1 plus e to the x to the negative 1 times e to the x dx. There you have something that's inside parentheses, so that kind of gives a hint that maybe that's a good thing to try for u. And then is the derivative of the thing inside popping out here as part of the dx? Looks like that might actually work. So that's a good thing to try. One other thing I wanted to mention, there's a function in the homework where the answer is capital F equals log of absolute value of 1 plus e to the x, which is a very interesting function, so I wanted to spend a little bit of time on it. What if the 1 plus wasn't there? That would be log of just e to the x. E to the x is always positive anyway, so you don't actually need the absolute values here. So then what's the log of e to the x? That's just x. And what values of x make it act as if the 1 plus almost isn't there? Well, if x is large, then e to the x is huge. Adding 1 to that doesn't really make much difference. And so log of 1 plus e to the x is basically log of e to the x, or x. So this is like when x is large. One plus e to the x is basically the same thing as e to the x approximately. So we can say log of 1 plus e to the x is roughly x if x is large. What if x is very, very negative? Like negative 10, negative 20, then e to the large negative is like e to the minus 10 or e to the minus 20, which is pretty darn close to 0. So then our function is roughly log of 1 plus 0, which would be log of 1, which is 0. So if x is large and positive, we're getting basically x. If x is large and negative, we're getting basically 0. So over here we have basically 0. Over on this side we have basically x. And it turns out to be a smooth transition between the two. So I know this looks exponential, but I'm trying to draw it as actually more like linear out in this way, out in this region. So it's a smooth transition between a flat line and a curved line, and a linear function. Some people call that a hockey stick kind of function, figuring that I'm not sure which way it goes. You could say the handle of the hockey stick is here, and then the curved blade of the hockey stick is going up this way, but it's actually linear. I'm not saying this is the only hockey stick shaped function, but it is one of the hockey stick shaped functions. So it's a smooth transition from flat to linear. So you might remember I've talked about the ramp function, which is exactly 0 until the origin, and then exactly a straight line. So this is a smoothed version of the ramp function. And it's also used in machine learning or stuff like this. It's called softmax. Remember the ramp function was max of 0, x. So this is also called softmax. Soft meaning a kind of smoothed out version of the max of 0, x. So useful in engineering when you don't want sharp transitions between operating regimes, useful in machine learning when we're doing softmaxes, all kinds of fun.